The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Thanks for coming out. This is going to be hardcore nonlinear spectroscopy bootcamp. We're going to try and make it through as much material as possible. My problem is I've got this week to do it, which means we're going to cram in as much as we can. And so here's what I was after, the kind of material that I wanted to go through, and we'll see how far we get. And one thing I forgot, in terms of scheduling, there's been a mistake with the scheduling tomorrow. I have a different lecture to give tomorrow at noon, so we won't be doing this at noon tomorrow. And instead, unless you hear differently from me by email, then just let's plan that the next one will be Thursday at 9 a.m. As scheduled. Okay. Okay, so I'm going to try and do as much as we can, and my feeling is sort of the top 75% of this board is probably what we'll get to. So the idea is I'd like to spend today, we're going to spend, I don't know, probably an hour and a half. We'll kind of break in between for 20 minutes or something like that, at least long enough to get some coffee. And what I'd like to work through is basically some introductory material and some formalism, which is what is nonlinear spectroscopy, why would you want to do it, and then talk specifically about coherent nonlinear spectroscopy, because that's really what the emphasis of this discussion will be. And then go through sort of just the methods that we use to describe what happens. And in particular, I think one thing that's very useful for getting into the business is diagrammatic perturbation theory. So then the good fraction of the remaining lectures are going to involve these next three topics. So in particular, we're going to spend a lot of time talking about third-order nonlinear spectroscopy, and I'll define that also. But that's the good fraction of methods that people use. And you can pretty much map the large fraction of things that everyone does onto this kind of a spectroscopy. And I'll try and point out that that means not just what is done in my group and in Keith Nelson's group, but that in fact what every spectroscopy group here on campus does. That's anything more advanced than stuffing something into an FTIR or a UV-Vis can be sort of mapped onto thinking in terms of third-order spectroscopy. And then a bit about two-dimensional spectroscopy. That is actually nothing new to that thinking. This is it's just a new way of thinking about old ideas in terms of a two-dimensional spectrum. And then, so that's sort of to refine kind of some of the prominent methods, and then how we're going to make use of those kinds of things. And this just in a very general sense. I'd like to give you a feeling for how we make use of these things in terms of studying molecular structure, molecular dynamics, and then for condensed phase problems, fluctuations and things. Okay, after that, there's some stuff that's up in the air. It's like, how far can we get? And also depending a little bit on interest. I have a feeling we're not going to be able to get any further than that this week. So if there's a lot of interest, we might be able to go schedule some other lectures later on. It'll have to be for quite a bit later on. And I was thinking something like coherent nonlinear Raman methods might be another good topic to go through. The influence of orientation and polarization on nonlinear spectroscopy is another big thing lots of people make use of. And then also surface selective nonlinear spectroscopy is also would be a great topic. And if you're really interested in that one, I think I would beat on the gentleman in the corner up there, because we'd like to coerce Paul into giving that particular one. By the way, I'm beating on Dave Blank from the University of Minnesota at the moment on giving the Raman one, because he's going to be giving the Modern Optics seminar in 2 weeks. And I told him, come early, give us a lecture, because he's a pro at those methods. So we'll see how this all develops. But an important thing is give me lots of feedback on, you know, what you like, what's important, what you'd like to see. All right. So let's see. Where shall we start? Okay, I guess a good spot is, what is nonlinear spectroscopy? What I don't want you to do is to get hung up in definitions about what it is, because it means many things to many different people. When you might ask, what's linear spectroscopy? And they're just sort of a working definition is that I want to understand how matter interacts with one incident light field on the sample. So spectroscopy in general, we just think of it as studying the properties of matter by irradiating it with light, which, you know, has a number of variables that we can control, like frequency and amplitude and polarization, phase, and so on. And manipulating any one of those variables and irradiating the system with one light field, that's sort of what we think of as linear spectroscopy. Okay, so what is nonlinear then? Well, it means many things to many people, and all of them are right. One is thinking that how one acts on the matter with the light field is not proportional to the intensity of the light field. So with traditional absorption, Raman scattering, and fluorescence methods, we think of how the matter responds as linear in the excitation light. And if you drive things hard enough, no, it's not. So that could be nonlinear. We can treat those effects with the things we talk about, but that's not what we're going to be dealing with. We're talking about the case where one interacts with the system using multiple light fields, each of which you can control independently, each of which you have independent control of things like time variables, frequency, polarization, phase, etc. Okay. And watching how the sample responds to that. In that, and you know, what may be a little confusing, we're actually going to use linear response theory to describe nonlinear spectroscopy. And this should not confuse you. What it means is that we will still treat the matter as responding linearly to a particular light field. But it may be that there are many light fields that come into the sample. And the nonlinearity arises from you know, the multiple fields. Okay. So that is what we're after. And to be a little bit more precise about it, not multiple light fields per se, but multiple light interactions. Because as you might imagine, there can be many interactions of the matter with just one of the incident fields. So that's what we're after. So to put this sort of into a more precise way of saying it is, you know, with linear spectroscopy, we can almost always just write the response of the system in some way as proportional to a matrix element squared. This says that a light field creates superpositions of, say, an initial and a final state, and our view into the matter is dictated by a matrix element squared. So, you know, writing this out a little bit more explicitly, we're always talking about two matrix elements, and for linear techniques, these are really just one is the conjugate of the other. And when we get to nonlinear spectroscopy, we're saying that we are going to have multiple matrix elements. That is, there will be three or more. And this means that there isn't sort of this nice, clean symmetry that one sees in the linear spectroscopies. Did you have a question? Okay. So, for instance, you might imagine things of the nature A, U, B, U, C, U, A. The moment you've got 3 or more, then you know you're in the nonlinear spectroscopy business. Okay. Right. Okay. All right. So I'd say then the next thing is why do it? So whoever came up with the term spectroscopy, I don't know who it was, but it's a brilliant name for how you understand, study light with matter, because spectron is the Latin word for spirit or ghost, and the scopian is to see, and so it's sort of implying, look, I'm trying to look at the spirit or the ghost of the molecule. And this is exactly, this really gets at everything that spectroscopy is about. You don't see molecules, right? We are not imaging. You study matter indirectly. You tease out information by shining light on it and watch and see how that light or how the matter is changed by that interaction. But you still don't know what those molecules are doing. Your ability to get information about the structure and dynamics of a molecule is really predicated entirely on a model. So we don't make enough out of this, but spectroscopy and modeling are inseparable, and one is the other. Okay. You don't always think about it that way. Very often the model is so ingrained in your way of thinking about it and so taken for granted that you just don't even think about it. Right? The fact that I have harmonic oscillator selection rules, that my vibrations are harmonic oscillators, or things like that. And that goes for basically any kind of spectroscopy. I would even say that for X-ray crystallography. You are shining light on matter, and you do have a model that you are fitting your observable to. It turns out that the constraints are very high in that case. You're going to put together a model, calculate an observable, and see how it matches. So every spectroscopy does this, whether you're thinking about it or not. Okay, so this gets at why to do it, particularly for really complex systems. So the more degrees of freedom you put together, we talk about this a lot for condensed phase problems, but it's just the same for many degrees of freedom in gas phase problems, that the more degrees of freedom you have, the more congested your spectrum becomes, the more difficult it is to interpret the relationships between different spectral features. And that's at the root of trying to get out the structure or the dynamics of the system. So what it really is about is developing more constraints on your modeling. And you can say this different ways. You can say it when I take a linear spectrum, it's ambiguous. I get a broad featureless line shape. I don't know how to interpret it. That's just another way of saying exactly the same thing, right? So, there's many ways of saying this. One is defeat inhomogeneous broadening. This is a topic that many condensed phase problems have to deal with. If I have a broad featureless line shape, what are the ways you attack looking at a spectrum? Well, there's always 3 observables. There's resonance frequency, and amplitude, and line width. Those are the kinds of things that we try to get a handle on. But in terms of dynamics, we're very often interested in line width. And the question is this telling me anything about dynamics? Is this really a homogeneous line, or is this really just a superposition of many molecules, behaving maybe quite differently? Regular spectrum doesn't tell you that. It also may be things about you're trying to establish spectral correlations. You know, so there the question is, okay, imagine I've got a spectrum that's got two resonances in it. And you go in with little or no knowledge. So there's an ambiguity in the spectrum, and it says, the fact that I have two peaks, how do I establish whether or not those peaks report on, let's say, one or two molecules, right? Do I have a resonance that arises from one species and a second resonance that arises from another? Or, in fact, do these two transitions both arise from the same molecule as the result of a molecular interaction? Or maybe other separate molecules, but do they encode some sort of a coupling? Right? So you could imagine having states, you know, A and B, coupling these together. This lead to, you know, new states 1 and 2. And sort of in an eigenstate representation, then we end up with the two resonances from these couple states. I can't distinguish those kinds of scenarios from a linear spectrum. So this is just sort of an example. There's many ambiguities that come from a traditional spectrum, and how do you get rid of it? Okay. Well, I think we'll see quite a few of those examples. Okay. Don't hesitate to interrupt me with questions. It'd be great to have conversation about any stuff that you don't follow. Okay. What we're going to spend most of our time on is coherent nonlinear spectroscopy. All right, so this is going to be a subset, you know, of what nonlinear spectroscopies are. So what do I mean by coherent nonlinear spectroscopy? In short, there's two ways of thinking how matter will respond once you've irradiated it with light field. And one of these we'll call coherent, and the other we'll call spontaneous. And it really just has to do with once you have used a light field to drive dipoles in your sample, how do they emit light? Or how do they respond to that light field? One of these possibilities is that they radiate all independently, and this is just sort of spontaneous emission types of processes. So, you know. And from that point of view, we would think of that as, you know, the intensity of light that we observe after the irradiation is going to be in some way proportional to sort of summing over the, you know, the radiation pattern from individual dipoles, individual independent dipoles, and it's going to depend on detection geometry and things like this. You know, and each one of these dipoles is going to follow just a classical dipole radiation pattern, something that looks, let's see, you know, the electric field will look something that is, you know, if I have a dipole aligned along, say, the z direction, then I'm really going to radiate light in an orthogonal direction. Okay, and so I get light emission from all directions. So what we're talking about for spontaneous spectroscopies are things like spontaneous Raman scattering, fluorescence spectroscopy, phosphorescence, those sorts of things. Okay, so okay, then. Coherent just refers to the case where we have an external light field. It acts to drive you know, let's see, imagine we have a light field incident on a sample. We have a sample that may have, you know, number of dipoles, but it drives each one of these molecules within your sample to creating a macroscopic phase-coherent polarization. That is, all of these dipoles are oscillating with a well-defined phase relationship. Macroscopically, there is an oscillating dipole we'll call the polarization, and that radiates a field. Remember that an accelerated charge radiates a field much like this, but now because of the phase relationship, there is constructive interference of all of these microscopic light fields in one particular direction. So there's we have a transmitted beam, but in addition there is, a signal that's radiated, and it has a well-defined direction, a well-defined wave vector. Okay. So this, actually, you may not have thought about it this way, but when you do an absorption experiment, it is a coherent spectroscopy in that sense. And we'll talk a little bit about this slightly different way of viewing absorption, that it really reflects a signal radiated by, coherently radiated by oscillators of your sample, which propagates collinearly with your transmitted field, but they're out of phase with one another, and this destructive interference is what you observe as absorption. It's just a slightly different picture of the same process. Okay. So we're going to be dealing with these sorts of coherent experiments, but also for the case where the polarization that's created in the sample arises from many electric field interactions. Okay, so nonlinear spectroscopy will be, we have a macroscopic polarization. It's created by many fields that enter the sample. They lead to a well-defined directional signal. That's radiated as a result of all those. And each of these fields then will be specified by some particular frequency, some time ordering, phase, and so on. Okay.
So is it a good picture to have a completely spontaneous system and a completely coherent system, or in any real experimental system, does one sort of, almost no matter what, have some degree of coherence,
yep,
even if you're using as incoherent light as you can make, and no matter what, you have some spontaneous emission, no matter how strongly you can polarize?
That's an excellent question. The idea is at all times, you always have both contributions. So when you put a light field into a sample, you will always have both spontaneous and coherent radiation coming out. As you might imagine, the degree to which I see one or another depends on how coherent their radiation is. So dephasing plays a really big role in determining how much of one or the other you get. In electronic spectroscopy in condensed phases, dephasing is an extremely rapid process, and hence you get fluorescence as the dominant emission process. And so spontaneous is, overwhelmingly, the large contributor in electronic systems. In vibrational systems, the fact that the radiative lifetime is so incredibly long and that intermolecular interactions are so much stronger means that they relax very rapidly non-radiatively, and that means that the response is almost always dominated by the coherent part. There's many cases where people have actually made use of the fact that you can look at both simultaneously and use that to deduce a lot of information about the intermolecular interaction. So if you look at resonance Raman scattering and compare the coherent and the incoherent scattering profiles, you can make a lot of use of that to tell you about dynamics. Yeah. The other thing that you were getting at, I'll talk more about this later, is that you tend to think of, say, I do a UV vis or an infrared spectrum with a lamp. You don't think of that as a coherent light source. Nonetheless, I'm calling that a coherent spectroscopy because it is true that the coherence of the incoming light itself, is scrambled very rapidly, but that light sets up coherent oscillations in the sample. And that's exactly what you measure when you do measure the interferogram in an FTIR interferometer, is you're measuring the coherence of the dipoles in your sample. Okay, so one thing I want to point out is that there's certainly spontaneous nonlinear spectroscopies, right? And I would say that there's lots of those that are done. It's, I detect my signal with spontaneous emission, say, or with some other sort of, maybe the sample reports somehow differently to you, photothermally or electron emission or something like that. Those would be coherent, but if you're acting on the sample with multiple fields and looking at the response, then that's still coherent. That's incoherent nonlinear spectroscopy. But we're going to deal primarily with this, and you'll see there's a real clear mapping from one to the other. Okay. Okay, I'd like to dig in a little bit into this formalism about what the nonlinear polarization is. That is, how do you set up a macroscopic oscillating coherently oscillating collection of dipoles in the sample. And so the polarization, we'll take it really to be a macroscopic property. It's basically an ensemble average, a macroscopic average over the dipoles of your sample. So we'll just really just take it as summing over all the dipoles in your sample, and those are just going to be distributed through space. M is just my count for a particular molecule in my sample, let's say. And for any one molecule, then there's going to be a molecular dipole moment, and we'll just take that to be a sum over charges within the molecule. Okay. So this is sort of our view of the dipole moment of the system and the macroscopic polarization. Okay. In the case of linear spectroscopy, we associate the polarization as related to the susceptibility times the incident electric field. So this is a frequency domain representation of how we describe the polarization. It requires an ensemble average over all of these dipoles, and that's expressed through a susceptibility, which is complex quantity. Its real and imaginary parts reflect the, the dispersive and absorptive parts of the response of your system. And this is just the frequency domain version of the linear response function that, and we've talked about that in 5.74. We can also say that this is related to it's really a convolution over the linear response function with the incident electric field. Okay? So the susceptibility and the linear response function, these are two identical manifestations of the response of dipoles to electromagnetic radiation, just one that's in the frequency domain, one is in the time domain. We would just get the susceptibility from a Fourier Laplace transform of the linear response function. Okay. Okay. So either of these methods are just used for, say, an absorption experiment. Okay. Okay. Now the next connection I'd like to make is the polarization to this radiated signal field. That is, how is it that an oscillating polarization acts as a source for a signal? And So the idea is we're used to talking about wave equations. Let's write one for a free electromagnetic wave, plane wave. So this is the equation of motion we'll write just for a plane electromagnetic wave propagating with a particular wave vector, oscillating both with a particular frequency and with a particular periodicity we call the wavelength. We solve that to get, our typical plane wave solutions. If we're trying to now talk about how such a wave gets radiated by a dipole, say in this form, we can think of this polarization now as a charge source. And if we talk about the acceleration of those charges, those will act to radiate a field. So we can really, rather than just saying this wave propagates in isolation, we can say instead that it oscillates as the result of a source. And that source is just the polarization. So let me see. Okay, so now here's my accelerating charges, and they're acting as a source for this field. And the solutions to this look very similar to the kinds of plane wave solutions that you're used to. We now say that there's the macroscopic polarization in the sample has a time profile and a space and frequency response that looks just like a plane wave solution. Okay. So we have a sort of a time profile to these oscillating charges. These oscillations have a well-defined direction and frequency, and that results from if you take this polarization, this leads to predicting, which way will this light field propagate, and that follows sort of a parallel solution. So here's the oscillating polarization. Solving this wave equation gives you sort of what the shape of the radiated signal is. And the wave vector of this polarization and the signal need not be the same. In fact, the relationship between these two sort of gives you the directionality of the signal. So let me go back over here. Okay. Now, when you calculate, when you integrate this equation over a macroscopic sample that has a length L, and where L is much greater than the wavelength of light, so you need it needs to be a large enough sample that you can have many oscillations of the field to establish constructive and destructive interferences between dipoles. But at the same time, we're working in the electric dipole approximation. So lambda is much greater than the sort of size of the molecular charge distributions. Okay. then you obtain this kind of a relationship between the radiated signal and the oscillating polarization in the sample. And the thing I want to point out here is that it depends on these phase matching terms here, where delta K is really the phase mismatch between the wave vector of the polarization and that of the field. And this just says there is going to be a well-defined direction. You know, I may have multiple incident fields that come into this sample with well-defined phase relationships. The net result of this will be that there is some net wave vector in the sample, and that is going to act as a source for a signal field whose direction will be sharply peaked, as given by this sinc function, in a direction given by the polarization wave vector. Okay. Yep.
I'm a little confused just thinking about a limiting case. If you had one molecule,
Yep.
then sort of by definition you have a macroscopic polarization. There's only one.
No, this really holds for an ensemble. So, I mean, there's actually a lot of interesting questions that come about, you know, can you have, or how do you see nonlinear behavior in a single dipole, or how would you see absorption in a single dipole? And that's something we won't get into. What we're talking about here, the idea of the phase matching and the coherent radiation that we're talking about is intrinsic in having a you know, large ensemble of many coherently radiating dipoles. So it I think in describing a single molecule behavior, you have to start from scratch and do this differently. So this is how we view the spontaneous is sort of how we would view the single molecule, you know, behavior. There's really independent radiation from each dipole. So right, this is by definition an ensemble approach. And that raises all kinds of interesting questions about how similar are the individual molecules to the behavior of the ensemble. Or how do you reconstruct that? Okay, so one thing that comes out of all of this, some bookkeeping, you will be able to keep track of, well, what direction does this signal go and what frequency does it have? And we'll establish that the wave vector of the signal is going to in some way be related to a sum or difference over all of the incident wave vectors into your sample. Whether that takes on plus or minus is going to depend a lot on whether you have absorption or stimulated emission processes, for instance. And this is really just a reflection of the principle of momentum conservation for the sample, and for the whole sequence of light interaction. And similarly, there has to be sort of an energy conservation statement, and that will be reflected by the fact that the frequency of the radiated light is going to be related to some sums and differences over the frequencies of the incident field. And this is, we'll also establish what gives rise to this energy conservation. A couple more definitions. So for our work, what we're going to be doing is working with a semi-classical description of the light-matter interaction. And what we mean by that is that this is all going to be handled by taking a Hamiltonian for the system to be a sum of two parts. One is a Hamiltonian that for the matter in your system, and we'll come up with various forms of what this Hamiltonian might look like, but the molecules are here, and then we have an external potential. This is the external light fields. They act on the molecules, creating coherent superpositions. And these light fields will just be treated like that, an external potential. We're not going to be calculating, how the matter changes the light fields. We are just going, and the matter will not influence them in any strong way. They just act on the matter. Okay, we're not going to be taking care of energy conservation between the matter and the light, for instance. Okay. And this external potential is going to be written sort of in the electric dipole approximation. It's going to be, related to the dipole moment of the sample and the incident electric field. Now, in general, I just want you to notice with this that when we say this, we now can mean this incident field is maybe the superposition of many different fields. Okay, maybe not just one. All right. Okay, and we're going to be treating a lot of this in the interaction picture that we developed in 5.74. Right? So that we're really going to be talking about the time evolution of the dipole moment of the sample. And remember, we've written that as time evolution of the dipole moment under the material Hamiltonian. Okay. And you'll notice this is not going to be the last time that I forget to put H bars in. I'm particularly forgetful with H bars. And okay, just for the record that I know them. And what we are going to do is assume that that there's just a direct correlation between the polarization and a non-equilibrium average over the microscopic dipole moment for the system. Okay. All right. Any questions popped up? All right. Okay, let's so now just to get started, let's talk a bit about just a linear absorption experiment and just sort of work through what hopefully is pretty comfortable to you. Did you have a question?
So you were just saying that the polarization is going to be, we're going to think of it as a time average of the, is that a time average?
It's a non-equilibrium ensemble average. Yeah. So I mean, we're basically, it's just another way of saying what I wrote up here, right? That at any moment in time you do an average over the position of all the charges in your sample macroscopically. And I'm using the bar for non-equilibrium just because I want to use this is the brackets as an equilibrium average. But it's basically how do the dipoles respond after you hit the equilibrium system, with the light. Okay. All right. So I just want to talk about this idea of linear spectroscopy as a coherent method. So back to, I've got a macroscopic sample. I'm going to have incident radiation come into the sample. I usually characterize it by some sort of an intensity, and that's related to the modulus squared of the electric field, and I'd like to sort of establish the idea that we're going to have an oscillating polarization, that those accelerated dipoles induced by the light field are actually going to lead to radiated light, And if you say that there's an incident wave vector to the light coming in, we want to establish that the outgoing wave vector is the same as the incoming wave vector. And it just happens to coincide with the wave vector for the outgoing, for the transmitted light, and that there's actually a destructive interference between these two fields that looks like absorption. Okay. So, and the way we measure that in a traditional absorption experiment is that, we measure intensities. There's the intensity of the outgoing light. That's just going to be some change delta I on top of the incident light. Okay. And I out is again related to the modulus squared of the well, let me see, yeah, sum over all the outgoing fields. Okay, so we've sort of established before that in a traditional picture of the polarization and therefore the radiated signal out of the sample is proportional to the susceptibility. So let's think a little bit about what the intensity of the outgoing light looks like. There's really two fields that are going to come out of the sample. There's the outgoing field, and then there's a radiated signal field, and we're going to observe the intensity, so the modulus squared of that sum. And this is going to, we know this sort of from our description here that I guess I didn't point it out before, but notice that there is an I out here. That means we've got a 90-degree phase shift between the oscillations of the polarization and the signal field. Okay. And I mean, that shouldn't come as, any big surprise. The biggest fields is when you have the fastest motion of the charges, and there's this 90-degree relationship with how fast, the charges are moving and the magnitude of the signal field. So what we're saying is we're just going to write this now in terms of the polarization in the sample. Okay. And now we'll make the approximation also that this transmitted light field, that the interaction is so weak that this transmitted light field is really not changed at all, that it's really identical to the incoming field. So this is approximately equal to the incident. Okay, and now for the polarization, this is just the susceptibility times the incident field. Okay, and so what do we have? Let's see if we sort of substitute, just recognize that the susceptibility is composed of a real and an imaginary part. And we substitute that in here and really evaluate all of our terms. The two leading terms, we can factor out the intensity of the incident light field. And the leading term is just 1. Next term is just twice the imaginary part of the susceptibility. And this just sort of confirms this idea we've, at least in 5.74, we've established this before, that it is the imaginary part of the susceptibility, the imaginary part of the response that tells you about the absorption of light, the absorption of energy from the light field. Okay. So, and this is why there's, even though there's all of these square relationships, between the fields and the intensities you observe, this is why there is a linear relationship between intensity changes and the response of the system. Okay. right. So how do we go about any questions? How do we go about describing this? As we go forward, there are many ways of dealing with the nonlinear response. In a time domain picture, it's very nice to treat it in terms of a response function. Right? So think of So the linear response function here, there's a step response to enforce causality, but it's related to correlation functions in the dipole operator. Right? The time dependence there is, as we've defined before, it's under the material Hamiltonian. But you can see that we have a couple of different correlation functions here. We sometimes write this as C minus C star. It's just the order of these operators. Now, if you're evaluating in linear response, this is an equilibrium ensemble average is performed over this product of operators. We might think of this as E minus En over C mu I. Sort of encoded in all of this is the fact that you're always keeping track of the evolution of at least two different coherences when you evaluate, how a system behaves. And sometimes we've written this also as, this may be a superposition of a wave packet propagating on the ground state of your system and on the excited state of your system. So keeping track of how the system evolves is already getting a little bit tricky here. And when you go to nonlinear spectroscopy, where you have to sort of establish what the phase relationships are between different coherences after another electric field is applied to the sample, bookkeeping starts to become really complicated. And this is part of the motivation for using the density matrix to describe nonlinear response. It becomes much more practical as a bookkeeping tool, and it also, for condensed phase problems, it turns out to have other advantages in terms of talking about dynamics. Okay, so now going back to linear spectroscopy, let's look at how we'd treat the dynamics there. Okay, so the equation of motion, rather than using the Schrodinger equation, we'll use the Liouville equation, so the equation of motion for the density matrix. I'm just being very explicit at the moment, it won't be later, that we're writing everything in the interaction picture. So that is the time evolution of this density matrix, follows just like the rest of the operators. And this is the interaction picture Hamiltonian, which also comes from the transformation of this interaction. Okay, the solutions to this, so there's another way of writing this also. G is a superoperator, and it just implies exactly the same thing, taking the commutator with this interaction picture Hamiltonian. Okay. So this is a time propagator. Now we can integrate this equation directly, and this sort of forms the basis for a perturbative expansion of the density matrix. And this is going to be one of the tools we make a lot of use of. And this is the origin of talking about what order is a particular nonlinear spectroscopy, how many light field interactions come into it. So I'm just doing a direct integration of this equation. T. This in and of itself is not a very practical equation because it is a function of itself. But this forms the basis for doing an iterative substitution of this equation into itself. And what you get is a perturbation series expansion, in which each term contains increasingly more and more interactions with the external light field. So the first order solution is really to suggest that this term here is just the equilibrium density matrix, and that you just have one light field interacting with the system, and then watch the response to that. Or if you're talking about nonlinear spectroscopies, then you perform this iterative substitution multiple times up to the order that's relevant for your purposes. And then at the end, what you're going to want is to let's see. At the end of the day, when you want to look at an observable and calculate the polarization you're interested in, you're going to trace over the density matrix and the dipole operator. Let's take the expectation value of the dipole operator at the end of all that. Okay. Okay. So I have to do it at least once. Let me write it out in its gory detail because we're going to use this quite a bit. In general, this perturbative solution can be written as a sum of terms that we'll write as, say, the 0th order, 1st order, 2nd order, and so on, expansion in the density matrix. Right. Rho 1 is the linear response. It should look just like our traditional linear response function that I just erased. And the idea is, the assumption in all these problems is that we're going to initiate the system in a state of thermal equilibrium. We'll call that rho EQ. And in fact, the 0th order density matrix is also rho EQ. And we're integrating over the time development of the system under one time variable, T1. Rho 2 is going to now look like a time-ordered expression. And it's going to involve nested commutators. Yep, that's fine. Okay. And so, I think you'll see sort of how this develops, that you have a, I guess one thing I should point out here is these time variables. In this linear case, as time progresses, we're going to make an observation of the state of the system at time t. And we're going to relate that to everything that preceded that time. We're going to do that by integrating over a variable T1. T1 is a time point preceding T, and that point is the point at which one interacts with the light field and drives the dipoles of the sample. And the behavior at T is just the integrated history over that single interaction. The 2nd order response just takes it a step further, but includes the fact that there is a specific time ordering enforced by the limits of this integral. That T1 must precede T2, which must precede the point of observation T. And we're going to integrate T1 up for all values up to T2 and say that first interaction must precede a second light field interaction, which must precede observing the system. Okay. So let's see, in terms of so we're going to make use of many of these terms, but now just going back briefly to the case of linear spectroscopy, you know, the polarization of the system, which is in turn proportional to the signal that you see. This just comes from tracing over the product of the density matrix times the first order expansion of the dipole operator and the first order expansion of the density matrix. We substitute this into here. T. Let's see, we're going to start the system at equilibrium, so our initial point is minus infinity. T1. Rho I. This is rho EQ. And now we can, let's see. Right, okay. Now we can manipulate things around a little bit. And also switch integration variables. The way we're going to label time variables is t's will refer to a point of interaction and a point of observation, and we'll use tau's as time intervals, the difference between those two. So let's define tau 1 as being t minus t1, and I'll let you do sort of the variable transformation here, and you can convince yourself after substituting minus mu I of T1 dot E1 what this looks like. And so just by comparing these, you can see we sort of recover what we expect as the response function. So this IH bar times the trace over the commutator and the dipole operator at time 0 and time t times the equilibrium density matrix. This is just the linear response function. Okay. So, okay, so we've written it this way. Now, just to wrap this part up, let me write this out explicitly just so we're clear about what this thing really means, because sometimes it seems to be a bit, abstract. Now, what we are saying there is that, the response function is really a sum over two correlation functions, C of tau minus C star of tau. And that correlation function can be written as a trace over the product of operators in the sort of traditional time-ordered direction. And if you're more interested in the wave vector representation, what we're talking about then is written in the eigenstate, system eigenstate representation. Same sort of thing. Okay. When you see rho EQ, that should just be telling you you're doing an equilibrium thermal average. And now the conjugate of this correlation function, we think of that as just replacing the time ordering as negative time, but sort of recognize that what that really looks like in terms of the density matrix is now the density matrix is sandwiched between two operators, and so this is sort of the start. And so in this case, it really refers to just flipping the order of operators in this thermal average. But this is sort of the start to how you think about keeping track of what's happening in the density matrix, which turns to be good for bookkeeping. Remember that one sort of starts with the system at equilibrium in some particular state, we call it the ground state. And now what you see is that this correlation function really reflects the fact that one is going to have time-evolving dipole operators acting either on the kets, the wave functions of the system, or on their conjugates. And that how the system behaves is going to depend on many terms, each of which differs sort of by phase relationships between which way is your dipole operator acting on the state of your system. For linear spectroscopies, that doesn't matter too much, but the moment you have more than one time variable to worry about, it's very important then to keep track of how the phase of how your system evolves between one time period and another. I'd like to now take the next step to talking about the nonlinear polarization. We're basically going to do the same thing that we did using the density matrix for the linear case. What I want you to identify is that in general, the polarization in the sample, if you treat this within the framework of linear response and perturbation theory the way we have, we can also then expand the polarization in orders of the incident electric field. And we'll be spending a lot of, this is sort of our bookkeeping. Linear spectroscopy is usually what we associate with linear response just in one field, P1. We're going to talk a lot about third order expansions. And what we mean when we write this is, we recognize that the polarization is just a trace over the dipole operator at time t and the density matrix, and that we can now do a perturbative expansion of the density matrix, and that maps directly onto the, what I've written up top here. So the terms we've got here are just these expansions in the density matrix, two different orders, each of which is just characterized by a certain number of field interactions. Now, made the mistake of erasing the other one. Let me just throw down the second order term again, just so that we have something to look at. This is the time-ordered interaction, nested commutators in field interactions. Okay. One thing I failed to mention earlier is that even though we are talking about a nonlinear response, we still talk about this as being linear response theory. So that there is still a simple linear interaction between how the system behaves when you have an interaction with one of these fields. The nonlinearity really comes about from the fact that there are multiple linear interactions. Okay. Okay, so what I'd like to do is connect this with a nonlinear response function, and that's really going to end up being the sort of the business end of doing nonlinear spectroscopy. It's really what we talk about as the kind of connection to what molecules are doing in the sample. And that, let's see, just one thing that you may have done or you may not have done, but is worth doing is to sort of just develop a classical description of a nonlinear response function, very much the way you would do it just for a linear response. Do you have a question?
The brackets are unbalanced in that it's not quite the same.
Sorry. Okay, should be okay now. Thanks. Yeah, keep me on my toes. I don't put 100% guarantee on what I write. So just in general, for any sort of form of, how a system would respond to multiple actions of an external potential, and you want to describe what happens at some time t as a result of what happened before it, you sort of expect that the change, in the expectation value of any sort of internal operator is going to it's going to have a lot of similarity to what we've written here. It just, really follows looks very similar to expressions that one gets from perturbation theory. So just in general, you say that, look, I'm going to define some sort of a response function. In this case, I'm going to have two external potentials, so I'm going to call it a second order response. And there's going to be some arbitrary form to what this external potential looks like, but I have independent control over both of them and how they act on the system. How my system looks at time t is going to depend on integrating over the full history of this system. And we are, through the limits on this integral, we enforce that this response function requires that this first field precedes the second field, and then we have to integrate over the full time history of those interactions. So taking this type of form of the response function, and then now comparing it to the, let's compare it, say, to the second order polarization, which we would get basically by inserting this expansion up into this term here. Let's see, maybe I should. Okay, so now what we're going to do is just explicitly insert what, the form of the interaction with the light field. In each case, it takes on the form mu dot E. Of course, the dipole operators are time dependent here. That's sort of what this is meant to express. And now we can sort of simplify this a little bit. And I'm going to do a couple of manipulations at the same time and let you sort out the details yourself. Switching variables as we did before. So let's see. Let me take it one step at a time. Now I've got to be careful. Okay, so what have I done here? One thing, so all I've done is a substitution, and then I've brought in this operator, and I've made use of something of sort of shuffling the nesting of operators. Just want you to remember that if you write nested operators nested left, that you can just switch the ordering, nest them right. And those are, evaluating those are equivalent. So I've done that over here also. And it's basically sort of to isolate our equilibrium density matrix. Okay. The next step is to switch variables. And it's here we have written the history of the system in terms of the time point of the interaction of the electric field. And we want to switch to time intervals between subsequent interactions. Okay. So what we're going to do is define these variables. We're going to say T2 is equal to T minus tau 2. Okay, so we're just trying to write time points in terms of time intervals. Okay, and T1 is going to be T minus tau 2 minus tau 1. All right. If you now rewrite just sort of this basic form of the response function, it sort of takes the form oops, let me erase this. Okay, so this is just sort of taking this general form and switching variables. And now we're going to do the same thing to our second order polarization. Let's see where I put that. Okay. Oh, no, this is going to be I over H bar. 0 to okay. So one thing I want to point out is, the integration limits now, talking in terms of time intervals, looks a bit simple, but we still have enforced causality over here. Just sort of by how we've written our time variables, we still enforce that tau 1 is a time interval that precedes tau 2. We have to integrate over the full history for all possible interactions prior to observing. So 0 refers to sort of the latest possible time, and infinity sort of the earliest possible, longest time interval before. In this way of looking at it, whatever the value of tau 2 is, you still have to integrate over all possible values of tau 1 prior to it. Now, comparing that to what you get from the second order polarization, what we have is something that looks analogous to what you see for a linear case. It's clear that this nested bunch of dipole operators is the second order response function. Okay. And so this is going to describe how the system evolves. Now this starts to look really messy, and at the end of the day, this is exactly why we have to start coming up with bookkeeping tricks, is that you can see that what this represents is that you have really, in this particular case, here, let me write the response function, explicitly. Now, when we write the response function explicitly, now we do have to remind you that you have to enforce causality. There's a step response here that ensures that the time variables tau are always positive. So what I want you to see here is you've got actually 4 separate correlation functions that are in this expression, right? We had 2 when we wrote out the linear response form, a dipole correlation function and its conjugate, its complex conjugate. In this case, we have 4 different correlation functions. They all just differ by the time ordering of these dipole operators. Okay. So let's, as you might imagine, this makes keeping track of everything that's going on a little bit complicated. Imagine going to 5th order. Okay, let's take a brief look at that. Let's see. Yeah, actually, let me, just to sort of make a little bit of contact to how we would write this in a wave vector representation. And the eigenstates of the system Hamiltonian. Right? Okay, just an equilibrium thermal average over this product of operators. Okay. Now, there is a time ordering enforced in this product of operators, and it may not be quite apparent there. So it's sometimes helpful to sort of piece this apart and take a look at them individually a little bit, just to sort of get a sense for what's going on. Let's see. Well, let's take one of the possible 4 terms that come out of this. Let's look explicitly at one that looks like, we'll call it Q1. And this looks like the trace. It would be the leading term when you expand all of these out, where you maintain the time ordering as it's written there. Use of all. Okay. So this says that we have a sequence of interactions with the electric field. There's a dipole operator that acts on the system, and then there's going to be some time evolution. This operator, remembering that when we write the interaction representation of the dipole operator, we're time evolving under the material Hamiltonian. Or alternatively, we can write that in terms of the time propagator U0. We have in between each of these interactions, we evolve for some period of time. Here's our first period of evolution, tau 1. This is the first time interval. And then there's a second time interval. This is whatever follows T1. That's tau 1 plus tau 2. So let's actually go ahead and write out the time propagation explicitly. Right? So what we got here is trace. Okay, here's really just writing out the time propagators and just a dipole operator. And the next thing we're going to do here is recognize that this product of the time propagator over both time periods times the time reversal operator for T1, this is just time propagation during the second interval. Okay. Let's see. And we'll also recognize over here that this product of time evolution during tau 1 and tau 2, this is just a product of two separate time propagators for the individual periods. Okay. And then the next thing we'll do is remember that there is a cyclic invariance to the trace. So that if we want to evaluate the trace of a product of many matrices, A, B, C, this is identical no matter how you invert the order, as long as you keep track of doing it cyclically. C, A, B, B, C, A. All right. So we're going to bring over this set of time propagators over to the other side. Let's see. Okay, so this is just a different way of representing, what is going on in the system. What this expression says is, when I perform an experiment, I begin at equilibrium in a certain state. That's this equilibrium density matrix. The next process is that there's an interaction with the light field. So step one is that my dipole operator acts on this state and creates a superposition with some other state. Then I evolve the system forward in time. So just recognizing that the time evolution of the density matrix then in its superposition state during tau 1 is just u naught of tau 1 times rho u naught. Okay. Then the second, so this second sandwich of time propagators propagates the density matrix forward in time. After that time period, we have a dipole operator here, and it acts from the left to the right on the density matrix. And then after that interaction, the system again gets propagated forward in time under u naught, this time where the time variable is tau 2, the second period. At the end of all of that, we multiply by a third density operator and trace over the matrix. Okay. So what is, when this sort of gets at how you read these sorts of processes, it reflects that there is a sequence of interactions and that there's free evolution of the system in the absence of light field in between those interactions. Now, what makes the different terms different. Let's take a look at that. Before I leave, I should also point out there's one other way of writing this kind of an equation. It's sometimes written, explicitly as a time propagator. Just remembering the solution to your Liouville equation. We can sort of encapsulate all that picture by writing it really in terms of a time propagator G, which sort of has this, that is the superoperator that involves a matrix. Okay, so now to compare terms, let's go to another one which varies a little bit by the order of these operators, the time ordering. So let's look at the next term in an expansion. Let's call that one Q2. And let's look at one that where we've got time 0 here on the left. Okay, now we can perform the same sort of manipulations. Okay. In this case, the first strategy is really just to move the 0 operator over here. The thing we have to remember is, in evaluating these things, is to enforce causality. That is, 0 has to precede tau 1, has to precede tau 1 plus tau 2. So in evaluating these things and then propagating the system forward, you have to make sure to enforce that. So the only way to enforce that this is the first operator is to act on the bra side, the bra side of the density matrix. So remember that this density matrix, you can think of it as this outer product. And this is equivalent to writing trace ui tau 1 plus tau 2, ui of tau 1, rho eq, mu I of 0. Okay, so now the action, as opposed to up here, where the dipole operator initially acted from the left to the right, acting on the ket side of this density matrix. In this case, it's the conjugate. So here, the dipole operator is acting on the bra side of the density matrix. And so this really just reflects the fact that we're keeping track of the fact that there are different possibilities for the permutations of the phase of how coherences evolve once you start to have multiple time periods. So this one is just reflecting interaction first on the bra side here, and then the second interaction is going to be from the ket side. Now, we didn't keep track of this for linear spectroscopy. It wasn't necessary, really. But now what this encodes is the fact that the way a coherence evolves, whether you talk about this as a positive or a negative complex exponential, whether you think about this as phase acquired, whether you think about this as positive time or negative time, we do, in different time periods, have to keep track of how one coherence evolves with respect to the other. Okay. So what I want to get at here is that each one of these correlation functions that you see there, they just differ by the time ordering of these interactions, right? And that Q1 is what we would call a ket interaction. Right? Both dipole operators act on the ket side of the density matrix. The phase acquired by the system is locked. It's additive. You propagate in the same way during the first period as you do during the second. Q2 is a bra-ket time ordering. If you write out the other two, you'll find that they are the conjugates of these two correlation functions. So Q3 is going to be a ket-bra, and bra-ket and ket-bra, these are just complex conjugates of one another. Q4 is going to be bra-bra. Okay, so in the case of linear spectroscopy, it was related to one correlation function and its complex conjugate. In the case of second-order nonlinear spectroscopy, the response is related to two different correlation functions that are distinct and different, plus their complex conjugates. Okay, and so we might, we'll also write that sort of in a form that looks like the second-order response. H bar out. That one. F equals 1 to 2. Q alpha to 1, 2 minus Q star. Okay. And each one of these Q's then is explicitly one type of correlation function of this form up here, just a time ordering of operators. Okay. All right. Any questions, folks?
So I have one sort of broad question about this kind of formalism. So I always feel like I understand this mathematically,
Yep.
but I have some trouble getting a physical intuition out of it because when I think of a real experiment, I think of lasers, which we haven't mentioned here, and I feel like, when you put specific times on this, it's almost as if these are delta functions of electric field.
Right.
Whereas, real electric fields, have some temporal extent, and
Right.
so how do we sort of translate from this notation
Right.
to thinking in terms of operators as, literally, equipment and observables as things we actually observe?
I agree with you. We're running through formalism now, which really has very little intuition until you start working through specific experiments. But as far as your question goes, in much the same way that you can come up with the time or frequency domain representations of linear spectra in terms of a susceptibility for the frequency domain or a response function for the time domain, there will be similar sorts of Fourier transform relationships here that allow you to cast the nonlinear response either in terms of a time sequence of interactions or in terms of products of multiple resonant denominators, if you like the frequency domain representation. So that's sort of a simple version to it, but what you're really getting at is actually encoded in this expression for the polarization, because that's really what these terms reflect. These are the shape of they're of arbitrary form. These are the shape of the electric fields driving the system. These could be brief pulses. They could also be continuous monochromatic waves. And those, you would necessarily have to enforce time ordering and act on those. And that turns into a Fourier transform then, right? And so we will go through some details, and I think that will help. Thanks.